from Hewlett Packard to tell us about mobile applications. But today I have the distinct pleasure of introducing you to Joe, who was seated somewhere here just a couple of decades ago. And he's going to talk to us about lighting. So let's welcome him.
All right, well, talking about modern lighting algorithms today. And it is one of my favorite topics to talk about. More innovation has happened in this topic recently than I think I can remember. There is lots going on, and the goal of today is to hopefully get you excited about lighting, share with you some of the algorithms being worked on today, and maybe hopefully get you guys working on it. So, the problem. How do we represent lighting as a simulation? You look around the room here, and there's all kinds of different objects, different materials, your skin, the table, the floor, the door, the projector. Everything is different. And light itself is just considered a kind of radiation that we can see with our eye. So it's very much tied to physics. It's very detailed in terms of every single object that light interacts with produces something unique, and it can be seen at the very finest detail. So when you go see a movie, when you play a game, you can see the differences in every kind of lighting simulation. You just don't realize it. It may look poor, it may look great, but not knowing how it works under the hood, to you it just looks like a great looking game. So there are two basic ways of solving lighting, static and dynamic. And I could have gone two ways with this presentation. I could have talked in terms of movies and special effects, or I could have talked in terms of games. And that line over the past couple of years is becoming more and more blurred due to amazing graphics cards, amazing technology. Stuff that are algorithms that are done in games are often seen in movies as well. So static lighting is when you take a scene that is not going to really change, so maybe a football stadium, for example, and you light the stadium as it would be lit at a certain time of day. At night, you'd have your stadium lights, and you can go in and you can paint the lighting contributions directly on your model. Dynamic lighting is the more popular kind of lighting nowadays, is when your entire scene is changing constantly. You have different lights, different objects entering your scene and interacting, and you calculate the lighting contributions on the fly, how something looks. So, and then there's non-real-time lighting, which I talked about, is basically stuff they do for movies. When you're not limited to 60 frames a second, you can spend lots of time rendering a frame, and you can put lots of computing power into it and make it really nice. So we're going to cover some very basic things to start out with. It doesn't do any good to go over these algorithms and not understand the tools that these algorithms use to make them work. So we're going to go over some graphics things, very briefly, very high level. Certain tools used in these lighting pipelines, and I'll give a brief overview of the DirectX 11 OpenGL 4.0 graphics pipeline, and then we'll start going into the various lighting algorithms. So graphics stuff. To start out, we have a vertex, which is just a point in 3D space. 3 floats is usually the popular way about going about that. You have a triangle, which is a plane in 3D space, which is made up of 3 vertices. You have a pixel, which is an RGB color, and an RGB is usually represented either 0 to 255 or in floats from 0 to 1. And then you can also have alpha in there as well. And then we have a frame buffer, which is a group of pixels. Very simply put, it's a frame in a game. When you say FPS, 60 frames a second, one of those frames comes from a frame buffer. And this is a very, very, very important tool that you're going to see throughout this presentation. Texture, I'm sure you all know what a texture is. It's a PNG, a JPEG, a group of colored pixels. A render target, which is a texture that you can render on, is tied to frame buffers. We'll get to that later. And then a depth buffer. This is a texture that's full of depth information. So every time you render your scene, there is a buffer that stores all of the relevant depth data. So it knows whether something is over, in front of something, and back of something, and it's used later on in the pipeline. So more graphic stuff. When you have a vertex and you want to transform it onto the screen, there are multiple stages of doing this, and each stage provides different abilities. So you have the model object space, and also you could consider this world space. So this transformation transforms a vertex relative to your object. So if you have an arm and you transform it 5 units away from your center, that's the object space. It's relative to where your object is. In world space, those transformations are relative to your world. So, your tank is 5 units to the left in your world. Those are often combined in your, model or object matrix. So then you have view space. This is a transformation that transforms a vertex relative to the camera. It's combined with this, you get the model view matrix, which transforms the vertex into view space, which is where is that object in the camera world. And basically, more technically, it moves the camera to the origin and sets up the scene at the origin relative to the camera. So, and then projection space is the final transformation. It takes your 3D vertex and puts it on your 2D monitor, your 2D screen relative to the screen's width and height. So yeah, that is basically it. These are all very important, and we will get to these very soon. But this is the DirectX 11 pipeline, and when you go to render something, it goes through this process. The data you provide goes through this process, and output is a frame. So we're not going to go over any of this stuff today. A geometry shader, a tessellator, a whole shader, domain shader. That is the new DirectX 11 stuff. So, and that's not really tied to lighting that much yet. Maybe soon. But you have the vertex shader, which does all of those transformations I just mentioned, transforming vertices into the various spaces, and ending up with the final transformed vertice. You have the tessellator, which we won't get into, geometry shader, which creates more geometry, and then finally the rasterizer, which you have your triangle in 2D space on your screen, marks those pixels, and then those pixels are run with the pixel shader, which is a small little program you can run on each pixel to do various things. And you can consider these to be functions. Just like in any program, they have input, they have output, and they have different functionality. Very, very programmable. So yeah, it's important that you have a firm understanding of these various stages. Because the better you know this stuff, the more creative you can get with your algorithms and leverage things like, the reason why I don't say, oh, this tessellation is not used in lighting, it's just because algorithms haven't leveraged it yet. It's less than a year old. So this whole portion of the pipeline is less than 4 years old. 4 years ago, geometry shader was brand new, and nobody was using it. So it's crazy to look at this and think that in the past 5 years, the shader pipeline has doubled in terms of processes and different things. So vertex shader, I think I've pretty much explained that. It's running each vertex in the scene, transforming the vertex data from 3D space into 2D projection space. And here is a sample vertex shader. It basically, you have a struct, which is, actually no, this is void, I changed it. So you take your input, and the data is defined in this semantic over here is defined as kind of what part of the pipeline is this coming from. And so that float 4 position is, what would you think that would be out of all the things I've talked about? Does anybody want to take a stab at that?
Pixel.
Anybody?
Vertex?
Yes, that's a vertex. So your vertex arrives in the position semantic. Rather than returning, there's various ways of returning values. So you just say out, and that's a return value, because a shader often returns multiple things in the pipeline. And so your result position is here, and that's also a position. And then you pass in, so these uniform variables are things that are consistent throughout the use of all of the vertex shaders. So you take your transformation, which I told you, the model view projection, you combine them all, and then you pass it in as one 4x4 matrix into all of your vertex shaders. And the result of a vertex shader usually is you do that transformation into screen space, like I said. So really quickly, let's show you what that looks like. So here you can see 2 models with vertices, and you can see there's some code in there to animate them. But it's pretty basic. You have model space. The view space is just the identity. There's no view transform. And then the projection space, which is taking those vertices and throwing them onto the screen. So pretty basic. So next is the pixel shader. After the triangles are in screen space, they are rasterized and pixels are marked, and then the pixel shader runs on each pixel. Here is an example. This one has a struct, but it's just a pass-through. So in the vertex shader, you can say, I want this vertex to have a color. And so that color output becomes the color input of a pixel shader, because it's just moving down the pipeline. And so if you wanted, you could say, I don't want the color to be that color, I want to return a different color. And then say this color that you pass in is green, you can set it to red, and then all the triangles will be red. So very basic so far. I hope I haven't lost anybody yet. Let's see. So a sample pixel shader. Let's see, here we go. So here you can see some green stars. That shader I just showed you is the pixel shader used here. There is a bunch of vertices that they're mapped directly to the screen, and then the vertex color is green, and the pixel shader just passes that green color through and returns it as output. So that is a basic example there. So, okay. So now you've gotten a crash course into a graphics pipeline. We've gone over some of the basic transforms, the basic shaders, and we're going to start expanding on these tools, and I'm going to show you a particular instance where this is used. So, deferred shading, many of you may have heard of it. It's used in a lot of games, a lot of different things. And when you render an object, you usually pass lights as input, and when you have 8 lights affecting one object, it's the old way of doing it was you would iterate through every light on that one object and render your lighting information on that object every time. And so if you had 20 lights and 50 objects, your execution time would be objects times lights, which is extremely intense. You could imagine in a game like today where you have thousands of objects in a scene. It can be very intense. And you want this to be quick because there's other stuff going on. So deferred shading is a more dynamic approach where you render your objects in the scene and you store that information in a frame. And then later on, you render your lights into the scene and you use that information that you rendered to previously as input. And then you render your lighting information and you get your final frame after that. So that pipeline that I showed you, remember I said you can render to a frame. So when you render a scene, you usually render it to the back buffer, and then you swap it, the OpenGL swaps it to the front buffer, and then you just rinse and repeat, and you constantly swap buffers. And that's how you get your multiple frames. But instead, what you can do is instead of rendering to the back buffer, you can render to your own frame buffer, divide up information, and then use that as input into a more complex equation, and then use that to input into your back buffer, and then swap. So that's what deferred shading does. It, let's see. So it uses a frame buffer object, and that's what it's called in OpenGL. In DirectX, I think they're just called render targets. You have a frame buffer which has several render targets. Remember, those are textures you can render to. And you render out different information of your scene, describing different properties that you later on use as input into your lighting equation. So here's a nice little graphic that I kind of whipped up. So you have your render object function, which calls render and goes in and starts the shader process, passes in the vertex data. You have what it's coined the G buffer. So this is all the information of your scene, and that position data is rendered here into an image. These are separate images. The normal. So a lot of you may have heard of the normal mapping. When you have a normal, that gets rendered here. I'll show you that and talk about that in a little bit. And then texture color. So if you have a brick texture on a side of your cube, that color gets rendered here. And so then you go into, you take all of these textures after they've been drawn to, and you attach them to your render light function, the spelling there, and then you render your light and use those as input to do your lighting equation. And so this is what a G buffer may or may not look like. So here you have, remember I said depth is how far something is in the scene. So this is kind of the same thing. A depth buffer in itself is just a 0 to 1, where 0 is the near plane and 1 is the far plane. So it's just represented as grayscale. So you can see these scenes aren't the same. These are different scenes. But here is a scene with like a house, and you see this house is far back. And then here's a scene where all the normals are rendered. So a normal describes which direction a surface is facing, very simply put. And that's described all the way down to the pixel level. So you'll notice that in this brick texture here, you'll see this crack, and that is defined in the normal map, where the normals are pointing in the direction that the light bounces off the crack. So, and you can see here's a normal map with like a little happy face. So, and then this is just an example. Like I said, you have a red texture, a brick texture, and you can apply that to the scene. So let's see. And one other thing. This is very customizable. So when light hits an object, a material, for example, a belt buckle, your belt buckle is very shiny, and it has certain properties that later on, if you go and learn about lighting, it's called specular light. And so you can take another texture and define different parts of a character or clothing that have different properties of light. So you can define the shiny part of a belt buckle differently than the leather and give it a different effect. And all that information can be stored in the G-buffer as extra descriptions for your equation. So here is a sample vertex shader for what it might look like. I think it's actually, no, that's the whole thing. So when you render your object, you need to render. You notice that I'm doing the same projection or the same transformation, but also I'm doing another transformation for my position texture for the render target, and I don't want that to be in projection space, so I just multiply it by the model view. And then there's some normal calculation down here, which is details, don't really need to worry about that. But you can see I make those appropriate calculations. So then here is the pixel shader for the G-buffer. So I'm taking all of that input that I just had from the vertex shader, and then here is some custom material values. I just gave it that name, probably not the best name. And then here are some uniform things. So the normal map is a uniform texture that I'm passing that's going to be ran on all the pixel shaders for the object I'm rendering. And so you can do, so shaders are highly optimized for this kind of stuff. So when you want to access a texture, they have functions that are implemented in hardware for doing that. So it makes it fairly easy to do high-powered computation. And since you're outputting multiple colors, because you're outputting to multiple textures, you output 3 colors. It's color 0, color 1, color 2. And that's just a semantic, much like these, where you can output multiple colors. So that's called multiple render targets, doing that there. And so yeah, before I show you the example, we'll go into here. So these 2 shaders give you that output, give you these 3 textures. And so then what you do is you use those as input into your light. So then when you render your light, you're basically drawing that light's contributions into the scene. And the vertex shader for a light is very simple. You're just transforming it into your scene, and you just move on. The pixel shader is where you take your input, where is my input? So this whole thing here is all the input. So you can see G-buffer render targets. Notice that I'm passing them in as textures. So we have the position, the normal, and it's called the diffuse for the texture color. So I'm passing those in as textures, and then extracting out the data as, my position is a float, my normal is a float, and then doing the various calculations in my lighting to get the different data. So diffuse light. I don't know if you guys will learn about that in graphics or not, but this is a certain kind of light that you can use. And this is a standard Blinn-Phong lighting model. There are tons of different lighting models out there that all do different things. And this one is one of the standard lighting models used. So when you're all done, you get your color, and that is your frame. But it doesn't stop there. There is post-processing that you can do, so blur effects, gamma correction, all kinds of different things you can do. Depth of field, I don't know if you've heard of that effect. All of those effects take place in post-process, which means that they can be applied in screen space. So you don't need to apply a blur effect into your whole scene when it's at this stage. All you need to apply a blur effect is maybe the depth buffer, so you use that depth buffer as input, and then you figure out what you want to blur, and then you can get depth of field or whatever you're going for. So, and that actually uses the pipeline just like I was talking about. So there's 3 stages at that point. You're rendering to your render targets, you're rendering to your post-process, and then you're rendering to the back buffer. So this pipeline doesn't necessarily mean you're rendering to the back buffer all the time. You could have 4 or 5 stages before you actually render to the back buffer. So I have a little example of this I can get into real quick. So here you can see a demo. It doesn't get any bigger. Here you can see a simple demo with a huge amount of lights represented as cubes. And they blend together nicely, and there's probably 200 or 300 lights in that scene. And with conventional forward rendering, there is absolutely no way you could do this in a fashionable, efficient way. So yeah. So now that you have a complex, and I hope I'm not moving too fast. I'm trying to stay within the time constraints here. But now that you have your nice, complex, deferred renderer, you can use this G buffer. And so, how many of you have heard of StarCraft 2? Yeah, okay. So StarCraft 2 uses a very, very similar G buffer, actually. Positions, so when you write to a texture, remember you only have 4 floats to write to. So what they can do is they can compress the position down to 1 float using some trig and window position magic. You can store the position of a pixel using 1 float. Since the x and y of the pixel is already determined, you can just store the z and then figure out where the pixel is when you're in your lighting shader. So by doing that, you have more room to store material properties. So depending on what the artists are going for, what kind of materials they want to represent, armor, metal, they figure out what kind of lighting model they want to use, and then they also figure out what kind of stuff they want to put in the G buffer. And then that's used later on in their lighting information. So in StarCraft 2, you'll find lots of instances where you'll see a spotlight on some guy's armor and it's flashing onto the scene dynamically. So if you keep an eye out for that, you might notice that. But Crysis, Unreal Engine, all of those game engines use some form of deferred shading. I want to pass this book around. Take a look at these bookmarks in the book and just pass them around, but this is where things start to get different. So depending on your requirements, depending on what you want to do, your deferred shader might be different than another guy's deferred shader. So, and this is where the innovation takes place, because people start to mess around with it and they discover more efficient algorithms, they discover more efficient G buffer configurations, and they start to discover all the different things you can do. And so deferred shading has been around for quite a while, but light prepass is a different form of the algorithm. This has been around for maybe 5 years. It was implemented in Grand Theft Auto 4. So there are many different forms of deferred shading. There's 2 of them are in that book, and it's a lot of people have been experimenting with it. So screen space ambient occlusion. So now I'm going to start talking about some other different algorithms that deal with adding to your lighting scene. So deferred shading can give you lighting. What I showed you can give you a basic lit scene, but you're still missing shadows. You're still missing global illumination. So global illumination is when you have objects reflecting light onto other objects. So that projector could shine light onto the wall, and then that wall reflects some of that light onto the floor. It starts to get really, really complicated. So in order to simplify and to fake it, we do things like ambient occlusion. So the best way to explain ambient occlusion, so anything with the word occlusion in it is basically shadows. So the best way to explain ambient occlusion is if you put your hands together and you look at the line where your hands connect, it gets darker as you do it. And so everywhere where there are crevices, you'll see black lines. And so that's because your fingers are occluding light as it gets closer together. So you can see here, there's a simple equation representing that. And you can store the occlusion value in pixels in a frame, just in a render target, just like I've shown you before. And then you can use that in a simple equation later to decide how much occlusion a certain pixel gets. So I have an example of that as well. Let's see if I can find it. Yes. So here is a Cornell box. So the Cornell box is very popular for testing lighting because it gives you shadows, it gives you different objects, and you can really see the difference in things. So there's all kinds of different things you can play around with this. This is just some demo I pulled off from NVIDIA's website. But you can see what I was talking about as two things come together, they start to occlude light, and it gives you various types of occlusion. And if we take out the color, that is purely the ambient occlusion contribution. So you can't get that with deferred shading, the stuff I showed you, but you can implement this as a post-process effect. And that's often, if you go into NVIDIA's drivers, they say, oh, well, we have, you can turn on ambient occlusion. It doesn't look very good because it's not naturally part of the game engine, but they do apply kind of a post-process ambient occlusion shader to stuff if you turn that on. So, and very, very recently has this evolved. So you can look on forums and see see forum posts from a year ago improving upon this algorithm. And it's really interesting because a lot of innovation is taking place in these specific areas. And everybody has access to it because it's just a bunch of guys playing around with this stuff. So, and also, Blizzard shared that information about deferred shading. They shared the information, they shared their G buffer, they shared their configuration, because all this kind of stuff comes from sharing the knowledge, and people are able to improve upon it. So, okay, continuing on. So that's human space ambient occlusion. There's a chapter in that book on it. If you're interested, you can check it out. So next is radiosity. And this is one of the, if not the biggest, global illumination algorithm around in terms of, it's been used in movies using ray tracing. In the past, that's been a non-real-time activity, but recently it's starting to become more and more real-time. And it's been used by Pixar and different guys to get global illumination. So putting radiosity on the GPU requires a lot of data structures and a lot of organization because, like I said, it uses ray tracing. And in order to, so basically radiosity is the algorithm which figures out how much light something has contributed to it from other objects in the scene, which is basically, like I said, what global illumination is. So if you have, so actually that image I showed you at the beginning, is radiosity. So you can see this cube this cube here is a white cube, and you can see the blue shining on it from here, and you can see the yellow shining on it from here, even though it's a white cube. So with deferred shading, you don't get that. With radiosity, you do. And so yeah. So in order to get radiosity, you have to construct. Let's see. Whoops. You have to construct your geometry in a way that you can quickly iterate through it and quickly figure out what when you. So basically, here actually, there we go. So you basically trace a ray into the scene, and you figure out where that ray hits. So a ray coming from that projector would hit the wall, and then it would hit the floor, and then actually it would hit under the table, and then the floor again, and go on for a long time. So you would construct it's called a bounding interval hierarchy. It's in that book if you go to that chapter. And you quickly traverse through the geometry and the shaders and figure out these hit points. And what do? You store that in a render target. So then later on, when you go, and actually this is so screen space ambient occlusion and radiosity are components of deferred shading. You can have a deferred shading pipeline and add radiosity to it. You can add screen space ambient occlusion to it. So I guarantee you StarCraft 2 has ambient occlusion somewhere in their rendering pipeline. So anyways, you write that information to a render target, and then in your pixel shader, you trace those hit points, and you figure out the color that when they hit, what was the color of the object, and you do your radiosity computation, and then you basically do you do your lighting model, and you include the ray tracing data from it, and you're able to get radiosity. So these are references, but I have a couple of examples. I don't know how we're doing on time, so I got like 10 more minutes here. So I want to show you the OpenGL debugger. So this allows us to step into a program and interactively look at some of the frame buffers that have that gbuffer information. It doesn't crash or run. Maybe. There we go. So here you can see our little demo that we used as reference earlier on, and I'm going to bring up the so over here you can see the OpenGL calls that were used. So GLU's program is used for shaders. GL active texture tells you what texture you want to bind, what texture unit you want to bind to. Bind texture tells you what texture you want to bind to. And then here's the swap buffers, which I was telling you about, which I've told the debugger to pause every time it gets to swap buffers, so we can look back at the frames that were generated. So let's see here. Hopefully it's not like so textures. There we go. So unfortunately, my graphics drivers aren't working right, but you can see some of these buffers. So here's the back buffer that I was telling you about, which got the frame before it's swapped. Here's the depth buffer, which doesn't have anything in it because, well, let's see, why doesn't it have anything in it? I don't think it has anything in it because this is the depth buffer for the back buffer, and since it's deferred shading, you have your own back buffer that you're writing to for all those render targets. So, which I think is, I don't think it's that one. I think it's that one. Which you can't see anything because it's weird. But anyways, so here are the frame buffer objects I was telling you about. So it has the G. This is technically this is the G buffer. This data is doesn't work right, so you can't really see what was in this texture. But you can see here that there was maybe some normals that were stored, or some information stored used in the lighting equation. So, like I said, each G buffer is different. So I can guarantee you that the configuration of this G buffer is not exactly the same as what I showed you in the slides, but it has those components more or less configured in a certain way. So, so yeah, that's one. And then I told you about post-processing and using things like gamma correction. So there's a shader in this demo that uses gamma correction to get the correct color off of a screen. Because when you output your data, when you output your frame directly to a screen, the color contrast and things aren't quite right. So you can use gamma correction to make it look better. So that's what is going on here. And so here's the render buffer, which is apparently not able to load. And one other thing I wanted to show you is the shader source code. So we can go and look. Let's see. So are there any questions so far? Yes.
Is Radiosity used in any high-profile games, or is it?
No, because it's the current stuff that they have right now is too expensive. The frame rates are not quite at what they need to be, and the demand is not quite there yet. Like I said, there's a lot of innovation in that area of finding the right data structures, finding the right configuration, putting those various things together. And actually, tessellation may also help. So it's very, very open at this point for innovation, for figuring out whether it works or not. But to my knowledge, no, I don't know of any game that uses Radiosity. I know just about every movie out there uses Radiosity because they can afford to spend the time to render it. But I don't know of any games that render it. No. Any other questions? Plenty of time here. So I wanted to show you the shaders, but this is being really let's try and read this here. So I encourage you, if you're interested in this kind of stuff, to not worry so much about the low level graphics. You should never ever have to deal with learning this stuff. You should try to avoid having to deal with these state function calls, because people have already done this work. That's what XNA is for. So I'm pretty sure you can. There's deferred shading implementations in XNA that you can download tutorials for and check it out and play around with it. And same for screen space, ambient occlusion. There's shaders and stuff for doing that. So, and if you want to get any of this, if you want to search any of this stuff, some good places to search are here. So gamedev.net. NVIDIA has SDKs, one of which I showed in here. ShaderX books, that book that's going around, has some of the algorithms that I talked about. OpenGL.org. This is if you're interested in OpenGL. And then MSDN also has some good stuff. So, so yeah.